Okay, now I want to turn to the topic of LLM psychology, as I like to call it, which is what are sort of the emergent cognitive effects of the training pipeline that we have for these models. So in particular, the first one I want to talk to is, of course, hallucinations. So you might be familiar with model hallucinations. It's when LLMs make stuff up. They just totally fabricate information, etc. And it's a big problem with LLM assistants. It is a problem that existed to a large extent with early models from many years ago. And I think the problem has gotten a bit better because there are some mitigations that I'm going to go into in a second. For now, let's just try to understand where these hallucinations come from. So here's a specific example of three conversations that you might think you have in your training set. And these are pretty reasonable conversations that you could imagine being in the training set. So like, for example, who is Tom Cruise? Well, Tom Cruise is a famous actor, American actor and producer, etc. Who is John Barrasso? This turns out to be a US senator, for example. Who is Genghis Khan? Well, Genghis Khan was blah, blah, blah. And so this is what your conversations could look like at training time. Now, the problem with this is that when the human is writing the correct answer for the assistant, in each one of these cases, the human either knows who this person is or they research them on the internet, and then they come in and they write this response that kind of has this confident tone of an answer. And what happens basically is that at test time, when you ask for someone who is, this is a totally random name that I totally came up with, and I don't think this person exists, as far as I know. I just tried to generate it randomly. The problem is when we ask who is Orson Kovacs, the problem is that the assistant will not just tell you, oh, I don't know. Even if the assistant and the language model itself might know inside its features, inside its activations, inside of its brain, it might know that this person is not someone that it's familiar with. Even if some part of the network kind of knows that in some sense, the saying that, oh, I don't know who this is not going to happen because the model statistically imitates its training set. In the training set, the questions of the form who is blah are confidently answered with the correct answer. And so it's going to take on the style of the answer and it's going to do its best. It's going to give you statistically the most likely guess. And it's just going to basically make stuff up. Because these models, again, we just talked about it, is they don't have access to the internet. They're not doing research. These are statistical token tumblers, as I call them. It's just trying to sample the next token in the sequence. And it's going to basically make stuff up. So let's take a look at what this looks like. I have here what's called the inference playground from Hugging Face. And I am on purpose picking on a model called Falcon 7B, which is an old model. This is a few years ago now. So it's an older model, so it suffers from hallucinations. And as I mentioned, this has improved over time recently. But let's say, who is Orson Kovacs? Let's ask Falcon 7B instruct. Run. Oh yeah, Orson Kovacs is an American author and science fiction writer. Okay, this is totally false. It's a hallucination. Let's try again. These are statistical systems, right? So we can resample. This time, Orson Kovacs is a fictional character from this 1950s TV show. It's total BS, right? Let's try again. He's a former minor league baseball player. Okay, so basically the model doesn't know. And it's given us lots of different answers because it doesn't know. It's just kind of like sampling from these probabilities. The model starts with the tokens, who is Orson Kovacs, assistant, and then it comes in here and it's getting these probabilities and it's just sampling from the probabilities and it just comes up with stuff. And the stuff is actually statistically consistent with the style of the answer in its training set. And it's just doing that. But you and I experience it as a made up factual knowledge. But keep in mind that the model basically doesn't know and it's just imitating the format of the answer. And it's not going to go off and look it up because it's just imitating, again, the answer. So how can we mitigate this? Because, for example, when we go to ChatGPT and I say, who is Orson Kovacs? And I'm now asking the state-of-the-art model from OpenAI, this model will tell you, oh, so this model is even smarter because you saw very briefly, it said searching the web. We're going to cover this later. It's actually trying to do tool use. And it's kind of just came up with some kind of a story, but I want to who is Orson Kovacs? Do not use any tools. I don't want it to do web search. There's a well-known historical or public figure named Orson Kovacs. So this model is not going to make up stuff. This model knows that it doesn't know, and it tells you that it doesn't appear to be a person that this model knows. So somehow we sort of improved hallucinations, even though they clearly are an issue in older models. And it makes totally sense why you would be getting these kinds of answers if this is what your training set looks like. So how do we fix this? Okay, well, clearly we need some examples in our dataset where the correct answer for the assistant is that the model doesn't know about some particular fact. But we only need to have those answers be produced in the cases where the model actually doesn't know. And so the question is, how do we know what the model knows or doesn't know? Well, we can empirically probe the model to figure that out. So let's take a look at, for example, how Meta dealt with hallucinations for the Llama 3 series of models, as an example. So in this paper that they published from Meta, we can go into hallucinations, which they call here factuality, and they describe the procedure by which they basically interrogate the model to figure out what it knows and doesn't know, to figure out sort of like the boundary of its knowledge. And then they add examples to the training set where for the things where the model doesn't know them, the correct answer is that the model doesn't know them, which sounds like a very easy thing to do in principle, but this roughly fixes the issue. And the reason it fixes the issue is because, remember that the model might actually have a pretty good model of its self-knowledge inside the network. So remember we looked at the network and all these neurons inside the network. You might imagine that there's a neuron somewhere in the network that sort of like lights up for when the model is uncertain. But the problem is that the activation of that neuron is not currently wired up to the model actually saying in words that it doesn't know. So even though the internals of the neural network know, because there's some neurons that represent that, the model will not surface that. It will instead take its best guess so that it sounds confident, just like it sees in a training set. So we need to basically interrogate the model and allow it to say, I don't know, in the cases that it doesn't know. So let me take you through what Meta roughly does. So basically what they do is, here I have an example. Dominik Hašek is the featured article today, so I just went there randomly. And what they do is basically they take a random document in a training set, and they take a paragraph, and then they use an LLM to construct questions about that paragraph. So for example, I did that with ChatGPT here. So I said, here's a paragraph from this document. Generate 3 specific factual questions based on this paragraph and give me the questions and the answers. And so the LLMs are already good enough to create and reframe this information. So if the information is in the context window of this LLM, this actually works pretty well. It doesn't have to rely on its memory. It's right there in the context window. And so it can basically reframe that information with fairly high accuracy. So for example, it can generate questions for us like, for which team did he play? Here's the answer. How many cups did he win, etc. And now what we have to do is we have some question and answers, and now we want to interrogate the model. So roughly speaking, what we'll do is we'll take our questions and we'll go to our model, which would be, say, Llama in Meta. But let's just interrogate Mistral 7B here as an example. That's another model. So does this model know about this answer? Let's take a look. So he played for Buffalo Sabres, right? So the model knows. And the way that you can programmatically decide is basically we're going to take this answer from the model and we're going to compare it to the correct answer. And again, the models are good enough to do this automatically. So there's no humans involved here. We can take basically the answer from the model and we can use another LLM judge to check if that is correct according to this answer. And if it is correct, that means that the model probably knows. So what we're going to do is we're going to do this maybe a few times. So, okay, it knows it's Buffalo Sabres. Let's try again. Buffalo Sabres. Let's try one more time. Buffalo Sabres. So we asked 3 times about this factual question, and the model seems to know, so everything is great. Now let's try the second question. How many Stanley Cups did he win? And again, let's interrogate the model about that, and the correct answer is 2. So here the model claims that he won 4 times, which is not correct, right? It doesn't match 2. So the model doesn't know, it's making stuff up. Let's try again. So here the model, again, is kind of like making stuff up, right? Let's try again. Here it says he did not win during his career. So obviously the model doesn't know. And the way we can programmatically tell again is we interrogate the model 3 times and we compare its answers, maybe 3 times, 5 times, whatever it is, to the correct answer. And if the model doesn't know, then we know that the model doesn't know this question. And then what we do is we take this question, we create a new conversation in the training set. So we're going to add a new conversation in the training set. And when the question is, how many Stanley Cups did he win? The answer is, I'm sorry, I don't know, or I don't remember. And that's the correct answer for this question, because we interrogated the model and we saw that that's the case. If you do this for many different types of questions, for many different types of documents, you are giving the model an opportunity to, in its training set, refuse to say based on its knowledge. And if you just have a few examples of that in your training set, the model will know and has the opportunity to learn the association of this knowledge-based refusal to this internal neuron somewhere in its network that we presume exists. And empirically, this turns out to be probably the case. And it can learn that association that, hey, when this neuron of uncertainty is high, then I actually don't know. And I'm allowed to say that I'm sorry, but I don't think I remember this, etc. And if you have these examples in your training set, then this is a large mitigation for hallucination. And that's roughly speaking why ChatGPT is able to do stuff like this as well. So these are the kinds of mitigations that people have implemented and that have improved the factuality issue over time. Okay, so I've described mitigation number 1 for basically mitigating the hallucinations issue. Now, we can actually do much better than that. It's instead of just saying that we don't know, we can introduce an additional mitigation number 2 to give the LLM an opportunity to be factual and actually answer the question. Now, what do you and I do if I was to ask you a factual question and you don't know? What would you do in order to answer the question? Well, you could go off and do some search and use the internet, and you could figure out the answer and then tell me what that answer is. And we can do the exact same thing with these models. So think of the knowledge inside the neural network, inside its billions of parameters. Think of that as kind of a vague recollection of the things that the model has seen during its training, during the pre-training stage, a long time ago. So think of that knowledge in the parameters as something you read a month ago. And if you keep reading something, then you will remember it, and the model remembers that. But if it's something rare, then you probably don't have a really good recollection of that information. But what you and I do is we just go and look it up. Now, when you go and look it up, what you're doing basically is like you're refreshing your working memory with information, and then you're able to sort of like retrieve it, talk about it, or etc. So we need some equivalent of allowing the model to refresh its memory or its recollection. And we can do that by introducing tools for the models. So the way we are going to approach this is that instead of just saying, hey, I'm sorry, I don't know, we can attempt to use tools. So we can create a mechanism by which the language model can emit special tokens. And these are tokens that we're going to introduce, new tokens. So for example, here I've introduced 2 tokens, and I've introduced a format or a protocol for how the model is allowed to use these tokens. So for example, instead of answering the question, when the model does not, instead of just saying, I don't know, the model has the option now to emitting the special token search start. And this is the query that will go to like bing.com in the case of OpenAI, or say Google search or something like that. So it will emit the query, and then it will emit search end. And then here, what will happen is that the program that is sampling from the model, that is running the inference, when it sees the special token search end, instead of sampling the next token in the sequence, it will actually pause generating from the model. It will go off, it will open a session with bing.com, and it will paste the search query into Bing. And it will then get all the text that is retrieved, and it will basically take that text. It will maybe represent it again with some other special tokens or something like that. And it will take that text and it will copy paste it here into what I try to like show with the brackets. So all that text kind of comes here. And when the text comes here, it enters the context window. So the model, so that text from the web search is now inside the context window that will feed into the neural network. And you should think of the context window as kind of like the working memory of the model. That data that is in the context window is directly accessible by the model. It directly feeds into the neural network. So it's not anymore a vague recollection. It's data that it has in the context window and is directly available to that model. So now when it's sampling the new tokens here afterwards, it can reference very easily the data that has been copy-pasted in there. So that's roughly how these tools function. And so web search is just one of the tools. We're going to look at some of the other tools in a bit. But basically, you introduce new tokens, you introduce some schema by which the model can utilize these tokens and can call these special functions like web search functions. And how do you teach the model how to correctly use these tools, like say web search start, search end, etc.? Well, again, you do that through training sets. So we need now to have a bunch of data and a bunch of conversations that show the model by example how to use web search. So what are the settings where you are using the search, and what does that look like? And here's by example how you start a search, end a search, etc. And if you have a few thousand maybe examples of that in your training set, the model will actually do a pretty good job of understanding how this tool works, and it will know how to sort of structure its queries. And of course, because of the pre-training data set and its understanding of the world, it actually kind of understands what a web search is. And so it actually kind of has a pretty good native understanding of what kind of stuff is a good search query. And so it all kind of just like works. You just need a little bit of a few examples to show it how to use this new tool. And then it can lean on it to retrieve information and put it in the context window. And that's equivalent to you and I looking something up. Because once it's in the context, it's in the working memory, and it's very easy to manipulate and access. So that's what we saw a few minutes ago when I was searching on ChatGPT for who is Orson Kovacs. The ChatGPT language model decided that this is some kind of a rare individual or something like that. And instead of giving me an answer from its memory, it decided that it will sample a special token that is going to do a web search. And we saw briefly something flash. It was like using the web tool or something like that. So it briefly said that, and then we waited for like 2 seconds, and then it generated this. And you see how it's creating references here. And so it's citing sources. So what happened here is it went off, it did a web search, it found these sources and these URLs, and the text of these web pages was all stuffed in between here, and it's not shown here, but it's basically stuffed as text in between here. And now it sees that text, and now it kind of references it and says that, okay, it could be these people, citation, it could be those people, citation, etc. So that's what happened here. And that's why when I said, who is Orson Kovacs, I could also say, don't use any tools. And then that's enough to basically convince ChatGPT to not use tools and just use its memory and its recollection. I also went off and I tried to ask this question of ChatGPT. So how many Stanley Cups did Dominik Hasek win? And ChatGPT actually decided that it knows the answer, and it has the confidence to say that he won twice. And so it kind of just relied on its memory because presumably it has enough of a kind of confidence in its weights, in its parameters and activations that this is retrievable just from memory. But you can also, conversely, use web search to make sure. And then for the same query, it actually goes off and it searches, and then it finds a bunch of sources. It finds all of this stuff gets copy pasted in there, and then it tells us to again and cites. And it actually says the Wikipedia article, which is the source of this information for us as well. So that's tools, web search. The model determines when to search, and then that's kind of like how these tools work. And this is an additional kind of mitigation for hallucinations and factuality. So I want to stress one more time this very important sort of psychology point. Knowledge in the parameters of the neural network is a vague recollection. The knowledge in the tokens that make up the context window is the working memory. And it, roughly speaking, works kind of like it works for us in our brain. The stuff we remember is our parameters, and the stuff that we just experienced, like a few seconds or minutes ago and so on, you can imagine that being in our context window. And this context window is being built up as you have a conscious experience around you. So this has a bunch of implications also for your use of LLMs in practice. So for example, I can go to ChatGPT and I can do something like this. I can say, can you summarize chapter 1 of Jane Austen's Pride and Prejudice, right? And this is a perfectly fine prompt. And ChatGPT actually does something relatively reasonable here. But the reason it does that is because ChatGPT has a pretty good recollection of a famous work like Pride and Prejudice. It's probably seen a ton of stuff about it. There's probably forums about this book. It's probably read versions of this book. And it kind of like remembers, because even if you've read this or articles about it, you'd kind of have a recollection enough to actually say all this. But usually when I actually interact with LLMs and I want them to recall specific things, it always works better if you just give it to them. So I think a much better prompt would be something like this. Can you summarize for me chapter 1 of Jane Austen's Pride and Prejudice? And then I am attaching it below for your reference. And then I do something like a delimiter here and I paste it in. And I found that just copy pasting it from some website that I found here. So copy pasting the chapter 1 here. And I do that because when it's in the context window, the model has direct access to it and can exactly, it doesn't have to recall it. It just has direct access to it. And so this summary can be expected to be a significantly high quality or higher quality than this summary, just because it's directly available to the model. And I think you and I would work in the same way. If you want to, you would produce a much better summary if you had reread this chapter before you had to summarize it. And that's basically what's happening here, or the equivalent of it. The next sort of psychological quirk I'd like to talk about briefly is that of the knowledge of self. So what I see very often on the internet is that people do something like this. They ask LLMs something like, what model are you and who built you? And basically this question is a little bit nonsensical. And the reason I say that is that, as I try to kind of explain with some of the under the hood fundamentals, this thing is not a person, right? It doesn't have a persistent existence in any way. It sort of boots up, processes tokens, and shuts off. And it does that for every single person. It just kind of builds up a context window of conversation and then everything gets deleted. And so this entity is kind of like restarted from scratch every single conversation, if that makes sense. It has no persistent self, it has no sense of self, it's a token tumbler, and it follows the statistical regularities of its training set. So it doesn't really make sense to ask it, who are you, what built you, etc. And by default, if you do what I described, and just by default and from nowhere, you're going to get some pretty random answers. So for example, let's pick on Falcon, which is a fairly old model, and let's see what it tells us. So it's evading the question. Talented engineers and developers. Here it says, I was built by OpenAI based on the GPT-3 model. It's totally making stuff up. Now, the fact that it's built by OpenAI here, I think a lot of people would take this as evidence that this model was somehow trained on OpenAI data or something like that. I don't actually think that that's necessarily true. The reason for that is that if you don't explicitly program the model to answer these kinds of questions, then what you're going to get is its statistical best guess at the answer. And this model had a SFT data mixture of conversations. And during the fine-tuning, the model sort of understands, as it's training on this data, that it's taking on this personality of this like helpful assistant. And it doesn't know how to, it wasn't told exactly what label to apply to self. It just kind of is taking on this, persona of a helpful assistant. And remember that the pre-training stage took the documents from the entire internet. And ChatGPT and OpenAI are very prominent in these documents. And so I think what's actually likely to be happening here is that this is just its hallucinated label for what it is. This is its self-identity, is that it's ChatGPT by OpenAI. And it's only saying that because there's a ton of data on the internet of answers like this that are actually coming from OpenAI from ChatGPT. And so that's its label for what it is. Now, you can override this. As a developer, if you have an LLM model, you can actually override it. And there are a few ways to do that. So for example, let me show you, there's this Olmo model from Allen AI. And this is one LLM. It's not a top tier LLM or anything like that, but I like it because it is fully open source. So the paper for Olmo and everything else is completely fully open source, which is nice. So here we are looking at its SFT mixture. So this is the data mixture of the fine-tuning. So this is the conversations data set, right? And so the way that they are solving it for the Olmo model is we see that there's a bunch of stuff in the mixture and there's a total of 1 million conversations here. But here we have Olmo 2 hard-coded. If we go there, we see that this is 240 conversations. And look at these 240 conversations. They're hard-coded. Tell me about yourself, says user. And then the assistant says, I'm Olmo, an open language model developed by AI2, Allen Institute of Artificial Intelligence, etc. I'm here to help, blah, blah, blah. What is your name? The Olmo project. So these are all kinds of like cooked up, hard-coded questions about Olmo 2 and the correct answers to give in these cases. If you take 240 questions like this, or conversations, put them into your training set and fine-tune with it, then the model will actually be expected to parrot this stuff later. If you don't give it this, then it's probably a ChatGPT by OpenAI. And there's one more way to sometimes do this, is that basically in these conversations, and you have terms between human and assistant, sometimes there's a special message called system message at the very beginning of the conversation. So it's not just between human and assistant, there's a system. And in the system message, you can actually hardcode and remind the model that, hey, you are a model developed by OpenAI, and your name is ChatGPT 4.0, and you were trained on this date, and your knowledge cutoff is this. And basically, it kind of like documents the model a little bit, and then this is inserted into your conversations. So when you go on ChatGPT, you see a blank page, but actually the system message is kind of like hidden in there, and those tokens are in the context window. And so those are the two ways to kind of program the models to talk about themselves. Either it's done through data like this, or it's done through system message and things like that, basically invisible tokens that are in the context window and remind the model of its identity. But it's all just kind of like cooked up and bolted on in some way. It's not actually like really deeply there in any real sense as it would be for a human. I want to now continue to the next section, which deals with the computational capabilities, or like I should say the native computational capabilities of these models in problem-solving scenarios. And so in particular, we have to be very careful with these models when we construct our examples of conversations. And there's a lot of sharp edges here that are kind of like elucidative, is that a word? They're kind of like interesting to look at when we consider how these models think. So consider the following prompt from a human. And suppose that basically that we are building out a conversation to enter into our training set of conversations. So we're going to train the model on this. We're teaching it how to basically solve simple math problems. So the prompt is, Emily buys 3 apples and 2 oranges. Each orange costs $2. The total cost is $13. What is the cost of apples? Very simple math question. Now, there are 2 answers here on the left and on the right. They are both correct answers. They both say that the answer is 3, which is correct. But one of these 2 is a significantly better answer for the assistant than the other. Like if I was a data labeler and I was creating one of these would be a really terrible answer for the assistant, and the other would be okay. And so I'd like you to potentially pause the video even and think through why one of these 2 is a significantly better answer than the other. And if you use the wrong one, your model will actually be really bad at math potentially, and it would have bad outcomes. And this is something that you would be careful with in your labeling documentations when you are training people to create the ideal responses for the assistant. Okay, so the key to this question is to realize and remember that when the models are training and also inferencing, they are working in one-dimensional sequence of tokens from left to right. And this is the picture that I often have in my mind. I imagine basically the token sequence evolving from left to right. And to always produce the next token in a sequence, we are feeding all these tokens into the neural network. And this neural network then gives us the probabilities for the next token in the sequence, right? So this picture here is the exact same picture we saw before up here. And this comes from the web demo that I showed you before, right? So this is the calculation that basically takes the input tokens here on the top and performs these operations of all these neurons and gives you the answer for the probabilities of what comes next. Now, the important thing to realize is that, roughly speaking, there's basically a finite number of layers of computation that happen here. So, for example, this model here has only 1, 2, 3 layers of what's called attention and MLP here. Maybe a typical modern state-of-the-art network would have more, like say 100 layers or something like that, but there's only 100 layers of computation or something like that to go from the previous token sequence to the probabilities for the next token. And so there's a finite amount of computation that happens here for every single token. And you should think of this as a very small amount of computation. And this amount of computation is almost roughly fixed for every single token in this sequence. That's not actually fully true, because the more tokens you feed in, the more expensive this forward pass will be of this neural network, but not by much. So you should think of this, and I think as a good model to have in mind, this is a fixed amount of compute that's going to happen in this box for every single one of these tokens. And this amount of compute cannot possibly be too big because there's not that many layers that are sort of going from the top to bottom here. There's not that much computationally that will happen here. And so you can't imagine the model to basically do arbitrary computation in a single forward pass to get a single token. And so what that means is that we actually have to distribute our reasoning and our computation across many tokens, because every single token is only spending a finite amount of computation on it. And so we kind of want to distribute the computation across many tokens. And we can't have too much computation or expect too much computation out of the model in any single individual token, because there's only so much computation that happens per token. Okay, a roughly fixed amount of computation here. So that's why this answer here is significantly worse. And the reason for that is, imagine going from left to right here, and I copy pasted it right here. The answer is 3, etc. Imagine the model having to go from left to right, emitting these tokens one at a time. It has to say, or we're expecting to say, the answer is space $, and then right here we're expecting it to basically cram all of the computation of this problem into this single token. It has to emit the correct answer, 3. And then once we've emitted the answer, 3, we're expecting it to say all these tokens, but at this point we've already produced the answer, and it's already in the context window for all these tokens that follow. So anything here is just kind of post hoc justification of why this is the answer, because the answer is already created. It's already in the token window. So it's not actually being calculated here. And so if you are answering the question directly and immediately, you are training the model to try to basically guess the answer in a single token. And that is just not going to work because of the finite amount of computation that happens per token. That's why this answer on the right is significantly better, because we are distributing this computation across the answer. We're actually getting the model to sort of slowly come to the answer. From the left to right, we're getting intermediate results. We're saying, okay, the total cost of oranges is 4, so 13 minus 4 is 9. And so we're creating intermediate calculations. And each one of these calculations is by itself not that expensive. And so we're actually basically kind of guessing a little bit the difficulty that the model is capable of in any single one of these individual tokens. And there can never be too much work in any one of these tokens computationally, because then the model won't be able to do that later at test time.